Hello everyone, today we're talking some more about eigenvectors and eigenvalues. I want to give some more examples and discuss some important properties. This is material from 5.1. So let me start by recalling the kind of main definition here. Remember our setting here is going to be A is an n by n matrix, so everything is going to be about square matrices. Then an eigenvector for A is a non-zero vector. Let's call it V, such that, right, when I multiply this vector times A, I get back a multiple of what I started. So this should be for some real number lambda. This has a name. This is what we call the eigenvalue. So again, just to start with an example here, let's do a little 2x2 example. Here's a matrix A, and let's take V1 to be 6 minus 5. V2, let's say, is 1, 1. I claim that these are both eigenvectors, and let's see what the eigenvalues are. So if I take A times V1, you can check that, well, this is A times 6 minus 5. Do the calculation, you get minus 24, 20. All right, this is a vector in R2, and notice that it's a multiple of what you started with. In fact, it's minus 4 times what you started with. So this is telling you that the eigenvalue, right, the lambda 1, let's call it, is minus 4. If you take 8 times V2, well, okay, that's 8 times 1, 1. You do that calculation, you get 7, 7. And again, that's a multiple of what you started with. So that means that V2 is an eigenvector. And what's its eigenvalue? Well, it's 7, because that's what I got. A multiple of 7 is what I got out when I multiplied. So let me just try to draw this usual picture here. Right, here's R2. What I see is that if I take V1, which is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, right, something like this. This was V1. If I multiply A times V1, I stay in the line determined by this vector, right? It's kind of off the page here. It's minus 4 times what I started with. And then V2, which is this vector, 1, 1, this also has the property that when I multiply A times this vector, I get 7 times 7 times what I started with. It stays in this line determined by V2. And what's kind of interesting here to tie this back into what we've been studying is that if I look at the collection V1, V2, well, this is two vectors in R2. And if I make a matrix out of them, I get a little 2x2 invertible matrix. So this is actually a basis for R2. And again, one way to see this is that if I take the matrix that I get by taking those as columns, this is an invertible 2x2 matrix. Right, but this, this matrix has a pivot in every column and every row. Therefore, it's a basis for Rn, in this case R2. And this will be kind of a theme going forward, that we have a basis for R2 where the elements, the vectors, are actually eigenvectors for a certain given matrix. And that's going to be a really important construction for us in the following weeks. Just kind of an example of that now. But we'll return to that later. I think for now what I want to do is just talk about kind of a bigger example. So we've only done kind of 2x2s. Let's do something bigger. And also I want to introduce some more notation. Notation and some terminology, I guess. So suppose A is this 3x3 matrix. And suppose I tell you that it has an eigenvalue lambda equals 2. Okay, so last time, recall from last time, that if I wanted to actually find an eigenvector, if we want to find an eigenvector, let's say V, such that, it actually realizes this thing. So if you want AV is actually 2V. Right, remember, you told me there's an eigenvalue, so there's some vector out there where this works. How do I actually find it? Well, finding that vector V was the same as solving a certain system, right, where I take A minus 2I times the vector V, the unknown vector, and I set that equal to 0, right? So a solution to this system where I have this as a coefficient matrix is the vector that I want, okay? So what I want you to do here is, well, let me just define. So the eigenspace for lambda, for any eigenvalue, is given by, well, let's use our fancy language, the null space of A minus 2I. So i.e., remember the null space is just a fancy way to say the solution set of the system, the homogeneous system, A minus 2I. Oh, so this is going to work for any lambda. I should put just lambda here. So A minus lambda I equals 0. Okay, so the eigenspace for a given eigenvalue is just by definition the solution set of this homogeneous system. So here, right, what are we looking at? We have lambda equals 2, and A minus 2I is given by, well, we take the matrix A, which is up here. Right, this was 4, 2, 2, minus 1, 1, 1, 6, 6, 8. And I'm going to subtract 2 times the identity, so 2, 0, 0, 0, 2, 0. And what I get is another 3 by 3 matrix. Again, all I've done is subtract 2 off the diagonal. So this is 2, 1, minus 6, 2, minus 1, 6, and then 2, this should be a minus 1, right? 2 minus 1, 6. Okay? So that's A minus 2I. And what do I want to do? I want to get the solution set for A minus 2I x equals 0. So we solve, this matrix becomes my coefficient matrix. I don't have to do this, but let's put in the zeros here because, there's this hidden augmented part. This reduces to, I'm going to press my magic row reduction button. These all disappear. These rows here disappear. I have a single pivot, okay? And so, what do I see here? So what is the actual solution set here? So, usual story. We do the same thing when we have a reduced echelon matrix. We get the solution set is given by, well, there's 2 free variables here. So it's going to be x2 times something. It turns out it's 1/2, 1, 0, plus x3 times minus 3, 0, 1. Okay? And this is your eigenspace, or lambda equals 2. And, again, this is the entire solution set for the system that we were interested in. So let me just point out, note that an eigenvector for lambda equals 2 is given by any non-zero vector in the eigenspace. Now remember, the eigenspace is all possible linear combinations of these 2 vectors. You could take 0 as both of your weights, but that would be the 0 vector. That's not an eigenvector. Okay. Also note just another thing I might ask you is for a basis. Well, a basis for the eigenspace here is given by, this is again a usual story. If I have the solution set of the homogeneous, it's always the span of a bunch of vectors. A basis would be the collection of vectors that I see, giving me those linear combinations. That's a basis for the eigenspace. And again, just a punchline from what we did in this example, and kind of something to use on your homework here, is that if I give you an eigenvalue, lambda, we can find an associated eigenvector, right? Which vector actually realizes that eigenvalue? What do? We solve the system A minus lambda I x equals 0, right? So this is a homogeneous system. We get the general solution. The general solution is given by A minus lambda I, the null space of A minus lambda I. This has a name. This is called the eigenspace. Okay, and then any, well, let's say for lambda, the eigenspace for lambda, and any non-zero vector is an eigenvector. Okay, so just to recap kind of the steps there, that we were given the eigenvalue, we solve this system. That whole solution set is called the eigenspace, and any non-zero vector is called an eigenvector. That's kind of what we just went through. Okay, so I want to end with some facts here. So further facts, I'll say, that we might talk more about in our discussion. So maybe fact one is that if A is a triangular matrix, then the eigenvalues are really easy to find. They are just the entries on the diagonal. Okay. Yeah, I might ask you to think about that. We might discuss it further, but let me just give you an example of kind of how this works. So, here's a triangular matrix. Why is this triangular? Well, everything below the diagonal is 0, right? And so the eigenvalues are just the things you see on the diagonal, 3, 0, and 2. Okay? So again, you can maybe think about why that might be the case. Another fact, maybe fact 2 here, is that it turns out, if you're kind of following along with what we've been discussing, is that a matrix A has an eigenvalue equal to 0. This is if and only if A is not invertible. Okay, you can also say singular. That's another way to say not invertible. Now, why is that? That is something that we've kind of already discussed kind of in the background. So note that if we know that AV equals 0 times V, well, that means that it equals 0 vector, right? If that's true for some non-zero vector V, then what do we know? We know that A times this non-zero thing is the 0 vector. In other words, then AX equals 0, the homogeneous, has a non-trivial solution. Right? And as you know, if you have a non-trivial solution of the homogeneous, that means, for instance, you have free variables, therefore the matrix is not invertible. Okay? And this actually goes the other way. If you have a not invertible matrix, if you have a singular matrix, you always have a non-trivial solution to the homogeneous, which then gives you an eigenvector with eigenvalue 0. Okay, so the last fact I want to just jot down, we're going to kind of come back to this, but I just want to write it down so we have it, is the following fact. If you have V1 through, let's say, Vk is a collection of eigenvectors where each eigenvalue is different. So you have a bunch of vectors. They're all eigenvectors, but each eigenvalue is different. Now, this one might have eigenvalue 2. This is eigenvalue -1, eigenvalue 0. They're all different. Then the collection turns out to be linearly independent. Okay, so this is an important fact that we're going to come back to. It should kind of remind you of this. Let me just go back. Well, before I do that, just, again, you have a bunch of vectors. They're all eigenvectors, but each eigenvalue is different. They all have different eigenvalues. Then that collection is linearly independent. And just to kind of finish things off here, that should remind you of this example here, where in the beginning, I gave you a matrix with 2 eigenvectors, and the eigenvalues were different, right? This one had eigenvalue -4, 7, and indeed, this was an independent collection. The 2 vectors were independent. This is kind of a very small example of that, but it's an example of this more general fact that we're going to make use of in the future. So that's it for now. We'll see you next time.